Okay, well, welcome back everyone. Today we're going to work on this little problem right here, and what we're told in this problem is that there's a rocket which is traveling at an altitude at which the gravitational constant is known to be some value of g lesser than that on the surface of the Earth. And we're also told the thrust force of the rocket produces an acceleration which is given along the axis of the rocket, and we're also told that at the position shown, the speed of the rocket is known to be some given value. And given this information, we're asked to determine the rate of change of speed of the rocket at this instant, as well as the radius of curvature of the rocket's path. Now, there are a number of different ways to tackle this problem, some of which involve the use of multiple coordinate sets, and some which involve just one. I'm going to choose to solve this problem using just one here. And to do this, what I'm going to do is I'm going to note that our E sub t direction is, of course, going to be aligned along the velocity vector. And our E sub n vector is going to be perpendicular towards the center rotation. Now, the reason I can actually solve this problem using one in particular coordinate set is I can go ahead and define now this angle here to be theta. And then if we do a little bit of vector projection and use the information we know about path coordinates, we can actually go ahead and determine the rate of change in speed and radius of curvature we're asked for. So in particular, what I'm going to do here is I'm going to note that in path coordinates, the acceleration vector is given by some v dot in the E sub t direction plus v squared, the speed squared, divided by the radius of curvature in the E sub n. And then I'm going to do something here and note that this acceleration vector has to be the net result of what we get from the a sub t component plus the net result of what we get from gravity. And so in this case, I can note that a sub t is simply the scalar a sub t in the E sub t direction. And I can add to that, in this case, a g, the gravitational constant, which is reduced due to the altitude. And I can project this back onto the E sub t and E sub n directions. So in this case, that g is going to be, let's do a little bit of math here. We're going to have minus times the cosine of theta in the E sub t direction. And I'm going to have plus the sine of the angle theta in the E sub n. And so now all I really need to do is equate the line here up above, and let me highlight that for you, this one right here, with the net result we get from right here. And so if I do that, of course, I get, the vector equation is going to give me two scalar equations. So if I look at, first of all, in the E sub t direction, I'm going to have that the rate of change of speed v dot is equal to at minus g times the cosine of the angle theta. And if I look at the E sub n component, I'll have that v squared over rho is equal to, in this case, g times the sine of the angle theta. So I can go ahead and solve these two equations and get the quantities we're asked for. So if I call this equation 1 and equation 2, of course equation 1 immediately gives me the answer we're looking for, namely that v dot is simply going to equal a sub t minus g times the cosine of the angle theta. And then if I take equation 2 and solve for the radius of curvature, I'll get that the radius of curvature rho is equal to the speed squared divided by g times the sine of the angle theta. Now, in this problem, we're given at, g, the angle theta, as well as the speed v. And so if you numerically make some substitutions here, you'll be done with this problem. I'll go ahead and leave that up to you to do. Best of luck as you work to solve this.